Morty, we've got to turn the project in early.
Hey everyone, how are we doing? It is Monday morning. Who's all here in the chat? We might do some Stat 1 projects, probably where people want to be at. Let's see right here. Here's the music folder. What's up, Roshni? Good to see you here. What do people want to do to start? It is your call. We got some work, some stuff to do. Stat 201 utk.edu. Stat 201 project. Let's see. Canvas content? Yeah, let's do Canvas content to start. Canvas content? What is that? Canvas content. You say it, we do it. Canvas content due tonight. 1.5. Oh, nice job right there, Blake. Let's raise some points. 1,000 points, Roshni. Here you go. Okay, so we got Canvas content starting up here at 2:45. Stat 201. Canvas content. Let's do it. Here we go. Main screen. Canvas content number 8. Confidence intervals. Okay. Who was the person who came up with the T distribution? Who was the person who came up with the T distribution? Does anyone know who came up with the T distribution? Who was the person who came up with the T distribution? Who was the person who came up with the T? Hold on. Who was the person who came up with the T? This guy. William Gossett of Guinness Beer. There he is, peering over at those beers right there with the T. T is basically like the normal. So it's plaque William Gossett. Yep, William Seeley Gossett, I think. There it is. William Seeley Gossett right there. There he is with probably a statistician. People go and check it out. All the stats people are like, oh man, we got to make our pilgrimage over to see the plaque of William Gossett. So there it is right there at Guinness Beer. And the T distribution, if you can't see right here, is a lot like the normal. The T looks almost identical to the normal. I'm blocking it right there. But it has with it, good to see you, Angel. It has with what are called degrees of freedom. Here, we'll show it again here real quick. Like the actual T distribution, because we've got a link to it if we just do !T. So when you think of the T, just think of the normal, think of z-scores. But the T is more exactly calculated. So the T distribution uses degrees of freedom, which for the one sample T are n-1. So if you have a sample size of 125, your degrees of freedom are 124. And the T will be very much like the Z. Like the Z-score for a 95% conf is 1.96. The T approaches that as degrees of freedom increase. It becomes more like the normal. So the whole point of the T is William Gossett found out that his intervals were not being calculated exactly. And then he started to run these tests and figured out that when you have a small sample size, you actually underestimate the variation in the distribution. So he created a correction, which can be modeled by the different T distributions. So you can look at where it's going to have more variation at lower degrees of freedom. The curve is more spread out. As degrees of freedom increase, the curve starts to go more towards the normal. And then you're basically using the normal after a certain point when there's enough degrees of freedom. A lot of people, when they're calculating this, will oftentimes just use the normal past like 100 or 200 degrees of freedom, but software will calculate it exactly for you, even to a ridiculous amount of degrees of freedem. We use websites like the tdistribution.com right here, not tdistribution.com, statdistributions.com, and the links in the chat right there to solve problems. This also has the normal and the chi-squared, which we already used the normal, and we use the chi-squared layer, which also has degrees of freedom with it too. Degrees of freedom tell you the shape of the distribution. As degrees of freedom increase, the chi-squared also becomes more normal. Chi-squared is an interesting one, a right skew distribution. So we will learn more about those later on. There's my background. And let's go here and answer the question that it was an employee at the Guinness factory that came up with the T distribution, which is going to be used for T-scores and T-tests and T-intervals. Good stuff. Which of the following would you not use to check in the nearly normal? Okay, so what is a normal probability plot? How do we read this? Who knows for 1,000 points in the chat? How do you read normal probability plot? What is a normal Well, yeah. Well, not the QQ straight enough, no outliers. Normal probability plot, we read backwards. So to memorize what this is, read it backwards. So it's a plot that shows you the probability your data is normal. I don't know the acronyms. So normal probability plots look like the following. If your data is normal, it follows that red line down the center. If it's not normal, it starts to deviate away from it. So with this, a normal probability plot is a plot that shows us the probability our data is normal. So it says, which of the following would you not use to check the nearly normal? Well, normal probability plots are used for that. We also have a histogram. When we think about what a histogram does, a histogram is going to be a univariate way to visualize data, and we can see if a histogram is normal or not normal. And also we have what is called a goodness of fit test. Comes back with a p-value where we'll put it associated with those. If the p-value is high, then the data, we do not reject the null, and we have good reason to believe it is normal, or we don't have reason to believe it's not normal. If the p-value is low, lower than 0.05, we reject the null and have evidence it's not normal. Now, all of this right here might be better shown by actually doing the work in Jump. I keep clicking the wrong button, but these things right here are important to know. So let's go over and analyze some quantitative data really quick right here and see what we have. Okay. So we're going to look at some quantitative data. So remember, we're seeing how to see if data is normal. So we're going to take the variable high school GPA. Let's go to Analyze, Distribution, High School GPA, and you notice it's blue right here. There it is. Blue means quantitative and Jump. And if you notice, it looks kind of normal. So that's the histogram, which is one way. So there's the histogram of it. A little bit of outliers, right? Outliers. And then we go over here. Then we go to quantile plot. Where is it at? Not quantile box plot. Normal quantile plot. There it is. Yeah, that doesn't look so bad. Yeah, look at that. Remember how we said if it follows that red line down the center? For those who can't see, we're talking about that red line down the center. And I would say, yeah, a little aberration right there. A little cluster data that went too much. Because bar charts are used for what kind of data, Blake? Blake's on the right track. So there's the normal quantile plot, the normal probability plot. Then last but not least, we go here to goodness of fit. And it's probably going to fail the goodness of fit because pretty much you get a large enough sample size power. Yeah, so it fails it. And so why is bar chart the answer? It does come back not normal here, but probably there's two tests, the Anderson-Darling and the Shapiro-Wilk, which there's two ways to do it. And Blake, you are a rock star right there. Blake knows that bar charts is not a way to check normality. Blake, we'll throw you some 10,000 points. Ridiculous. Great answer. That's the exact answer I was looking for. Bar charts are not something we would use to check normality because bar charts are for categorical variables. So if we go to graph builder, drop something like gender right here and go to bars, well, this is when we do, and there's bars right there, or there's bars right there. Bar charts are categorical data and are not used to check nearly normal because it's categorical data. So great answers right there. We do not use bar charts. Remember, quantitative data can be checked with the normal probability plot. Quantitative data makes a histogram. Quantitative data does the goodness of fit test. Bar charts are for categorical data. Decreasing the sample size will make the margin of error a smaller value. So let's look at two of our intervals right here. It says decreasing the sample size will make the margin of error a smaller value. We'll take it right here so we can see it while we do it. Okay, there it is. And let's look at an equation for this. So when you think about the equation we've learned two so far, and the equations we've learned are p hat plus or minus z p hat q hat over n square root. Then we have y bar plus or minus t star, and that has a star too, n minus 1 degrees of freedom, which is a subscript to tell us the amount of degrees of freedom for the shape of the t, and then also s over square root of n. So these are two separate equations right here. The top equation is a confidence interval for the true proportion created from the sample proportion. The bottom one is a confidence interval for the true mean created from the sample mean. Speaking briefly on these, you should know all the notation. So if you're watching this right now, write down each one of these as I say it. So I'm going to tell you what it is. I'm going to highlight it. So let's start here with p hat. P hat is the sample proportion, which would say something like blank percent of people in our sample said they eat at Taco Bell, but it can also be found with X over N, X being the number of successes, N being the number of trials. So we could say like 40 out of 200 people ate at Taco Bell. So P hat would be 20%, 40 over 200. P hat is the sample proportion. Z star is the Z score relative to the percent confidence. So if they say make a 95% confidence interval, it'll always be 1.96. If they say make a 98% confidence interval, it'll always be 2.3263. And you can find these values by going over to the David M. Lane right here, and then putting in the second button, going to 98% and clicking between, and there's the 2.3263, and these are the z-scores relative to the percent confidence. We put a star on them. That's very important to see because that means relative to the percent confidence. P hat, once again, is the sample proportion. Q hat is the complement of P hat. So if P hat was found to be 0.2, Q hat is 0.8. If P hat is 0.3, Q hat is 0.7. Q hat is found by the formula 1 minus P hat. N is the sample size, which would be something like we talked to 200 people. Good morning, Meredith. We're talking about the notation right here. You got to know the notation. And here's the confidence interval for the true mean created from the sample mean. So this would be something like from our sample, students had a GPA of 3.8 for the 100 students we talked to. So the sample mean Y bar, putting the bar over it, means mean of that variable. T star means the T value relative to the percent confidence. So what we do right here is we go over to the T app. I'll put the T app in the chat again. And you have to go in and do the same thing we did with the David M. Lane, where you go over here to the T applet, make sure you're on the T. You need to know your degrees of freedom for it, which are going to be N minus 1, sample size minus 1. So if you have a sample size of 57 degrees of freedom, I like to use this right here where we graph between, and you do 95% confident, 90% confidence, whatever it said in your problem, and then you can see the middle areas graphed. And this is the T star right here. This is the T star relative to percent confidence that the problem tells you to solve or you wish to make with N minus 1 degrees of freedom. And that is for the one sample T. It has N minus 1 for the one sample T. Degrees of freedom tell you the shape of the distribution right here. So depending on the degrees of freedom, like if we go up in degrees of freedom, it's going to go more towards the normal, or if we go down, it's going to be more spread out than normally. Just know, yeah, and Justin, good point right there. And we were talking via email, Justin. You might be on a different account. I can add you back right there to your mod status if you want, Justin. It's a different degrees of freedom formula for the 2 sample T, and we were talking about some interesting stuff with that. How there's some really easy ways to remember it. And yeah, Justin, good comments right there. And then also here we have the sample standard deviation, which in a problem would say something like the variation in GPAs was found to be a standard deviation of 0.4 for the 100 students we talked to. It has to be from a sample, and it's the standard deviation from a sample. And then this is the sample size. So what did the question ask? Decreasing the sample size will make the margin of error smaller. So it says decreasing the sample size. So if this goes down, we're dividing by a smaller number. So you can plug in numbers. This might be the easier one to work with. So if we plug in fake numbers right here, the margin of error in the interval is everything over here. So this is all the margin of error of the interval. Everything from here over, as in everything here. The other side of it is the estimate, which is the center of the interval. And so what happens when margin of error decreases? Well, if margin of error decreases, we're dividing by a smaller number. So let's put in a T of 2 just to solve a problem right here. And let's put in an S of 10, and we'll do square root of 100. And you can see here, the problem solves out right here to be 2 times 10 over 1 square root of 10, which is going to be 2 times 10 over 10, which is equal to 2. So that's one example of solving it out right there. It's 2. Now let's decrease this and see what happens. So if we go here and do 2 times 10 over square root of, let's say, 4, which is a much smaller, now we decreased it. So that's a smaller sample size for n right there. Now we get the following. Now we get 2 times 10 over 2 is equal to 2 times 5 is equal to 10. So if we look at what happens when we decrease this sample size, decreasing the sample size from 100 to 4 made a larger margin of error. So the margin of error got larger. And think about that. Theoretically, if you take a smaller sample, you would have greater error. So this is definitely false. And I do want to point out, I know I took a very long time to say the answer is false. This right here is the key understandings. So take a moment and maybe rewatch the video if you need, but write down what each one of those things are. Know what the equations are. You do get a formula sheet for the test, but know what the notation is. Know how to understand what the problem's asking. Because if you get to a problem, it's like the margin of error. You're like, well, where's the margin of error in the problem? So you have to know where the margin of error is. It's everything after the plus or minus, and that's a huge help. So decreasing the sample size will make the margin of error smaller. No, it'll make it larger because you have more variation or less understanding of your data, we should say. A confidence interval for a confidence interval of a population portion that has the limits of this and this. What is the margin of error? Can you do it? Oh, there's an interesting round on this one. I really wish, and it wants it as a percent. I really wish, and I'll tell you why. I really wish the bottom of this interval was 60.7. What is the margin of error now? We'll talk about how to find it. There's a really quick way to memorize what the margin of error is. I'm changing the problem slightly to make it way easier to solve. And it might even give it to us with the plus or minus on the problem. The problem might have a little give on it. But can you find the margin of error right now? N is sample size. N is sample size, the amount of sample we take. You rarely do. Some of my Pearson problems have you back solve for it to be like, what sample size would you need? Like sometimes in my Pearson problem might say, if we have this and this parameter for our problem with this margin of error, what sample size would we need to achieve this goal? Usually in our problems, we just say to you, the sample size they took was this. How do we find margin of error? I was trying to calculate me, but I need, and I did not see it. You might send me the problem. Send me the problem, I'll take a look. Yeah. Because you can calculate, like when we did some problems like that last week. What assignment we were going over? Have we gone over the quiz? Oh, we're doing the Canvas content right now. We can do quiz 14 too. Whatever you want. Whatever you want. How would we find the margin of error of this? Oh, Blake, are you asking about this one? Are you asking about this one right here, Blake? Or are you... So, but this one only wants us to find the margin of error. What is... Like, when we talk about conceptually, this is a good thing to memorize. If you look at the equation, P hat is at the center of the interval. So that's the center. The margin of error is a plus or minus. So the margin of error, great job, Tara, right there. Exactly. And so Tara, great work. That's what I want you to be thinking about. And you've done it, Tara. Tara knows how to theoretically solve this. We'll show this here in a second. Let's throw some points. The margin of error is what the length of the interval. Like, memorize this. The margin of error is what the length of the interval. The margin of error is always what the length of the interval. So the margin of error is always what the length of the interval. So think about the length of the interval is this, and the margin of error is what the length? Half the length of the interval, right? So the margin of error is half the length of the interval. So look at what I did to the problem to try to make it easier. What is the length of the interval now? Which just don't try to solve it exactly right now. Just look at it and be like, oh, that interval is this % long. It's a good way to like kind of understand that you got the problem right. The margin of error or the length of that interval is what? Currently on the screen, how long is that interval? 60.7 to 70.7. How long is that interval? Like how going from 60.7 to 70.7, how long is that? 10. So what would be the margin of error then? So if the length of the interval is 10, we'll use nicer numbers over here. So if this started at 60 and went to 70, then the margin of error would be 5. That's because you'd go plus 5. And great job, everyone. And once you start to see things like this, you get faster at solving them. And you're like, oh, the margin of error is half the length of the interval. But the formula for this, if you want to solve it here, would be, and let me make you a mod again, Justin. I don't know if you're on a separate account. Check to see if you're on a separate account, Justin. Upper minus lower divided by 2 equals ME. There's also the formula upper plus lower divided by 2 equals center. Because if you average the numbers, like 60 plus 70 divided by 2 is equal to 65. That's the center of the interval. Where if you take 70 minus 60, that's the length of the interval, which is 10. So you get 10 over 2, which is equal to 5, which is the margin of error. Just understanding some math like this is very important. And to see it up here, to know that we have the upper and the lower and the center of the interval. There you go. There's some really good math. So we can go back over here and apply the same logic. I had a student tell me, I can't solve this. Where's my sample? Like, I've had multiple students on tests be like, I can't solve this. I don't tell them during the test, but we go upper minus lower. There's the distance of the interval, divide by 2. Whoops, divide by 2. And there it is. It says round to 1 decimal. So it may have given us if we did that. A confidence interval is made from a what to estimate the truth for a what? I am 95% confident that the true, what would we say, sample or population is contained in the interval? What is the confidence interval trying to contain? And then you can also see in the equations, I am blank percent confident contains the true, and then the true means for the what? For the sample or for the population? When we say true, for the population. So what is at the center of the interval? At the center of the interval is what does that stand for right there? And true means population. What's at the center of this interval? What's at the center of that interval right there? Like at this interval right here, what's at the center? We're doing it as a percent right now. What does that notation mean? And what is p hat? You are correct, Meredith. Great work right there. What is p hat? What does that mean? Sample proportion, right? So the sample proportion is at the center. So the confidence interval is made from the sample to estimate. I am 95% confident the true proportion of students who eat at Taco Bell. And when we say true, we're talking about for all, which is the population. The true proportion of students who eat at Taco Bell is contained in the interval 60 to 70%. I just made up some fake context for that. But it means the confidence interval is made from the sample to estimate the truth for a population. I think we should be good right there. Should we do one more version of this, or should we go over to quiz, whatever it was, quiz number 14? What should we do? Should we do one more quick version? We might go a little quicker this time because we've already answered many of them. But what would people say? Take a vote right now. They changed my voting thing. One more. Let's do one more real quick. Here we go. Let's do it. And quiz 14, we'll do quiz 14 next. Speed run it. Quick version. Let's do a quick version, and then we'll do quiz 14. When doing confidence interval for the mean, we use the following distribution to calculate the number of standard deviations needed for our confidence. Ooh. That is a little... I gotta talk to Terry about this. Let me take a screenshot. I know the answer. But I'm gonna send him a quick email. Say, shouldn't this say standard errors? 2 seconds. Set to one, update a question. Shouldn't. Okay. There we go. Okay. So, Mr. T is mean. So when we do confidence intervals for the mean, he's a nice guy, I'm sure. Unless you're doing drugs, and he's very mean. Check out those 80s commercials. He means business. He's a good father guy. He knows how to keep you straight right there and make sure you're following, you're doing the right things, keep you on that path, following along right there. So you need to stay in line with Mr. T. No, Mr. T says no to drugs. What's it they say? Like, stay on that path right there. Follow it. He knows how to keep you doing what you should be doing. So, yeah. Good stuff right there. So, right here, which of the distributions do we use with the mean? T, Z, chi-squared, what are the other ones? T, Z, chi-squared, skewed distribution. Which ones do we use with the T? Which of those do we use with the T? T. Boom. Right there, we see it. Oh, where is it? There it is right there. The T right there. Mr. T. I feel like I have to show that commercial. Anytime I say Mr. T is mean, because I say Mr. T is mean to connect the idea of when you're doing stuff with means. There, we'll do it like when you're doing stuff with means, you use the what distribution. When you're doing stuff with means, you use the what distribution. So when you're doing stuff with means, you use the what distribution. When you're doing stuff with means, you use the what distributions. When you're doing stuff with means, you use the what distribution. So many like re-uploads and stuff of it. No one knows?
Makes me mad. I get angry just thinking.
No one knows? When you're doing stuff with means, you use the what distribution. When you're doing stuff with means, you use the what distribution. T distribution, yes. That's why Mr. T is mean. I'm sure he's a nice guy, but this is what Mr. T thinks if you're doing drugs.
I get angry just thinking about it makes me mad. Little kids doing drugs, it turns my stomach.
Jeez. He's not happy with you. You doing those things? He's not happy with you.
Don't, or else.
Right there. Juggling. So yes. Is he at a Waffle House? He might be. This is my favorite moment of any PSA from the 80s/90s.
It turns my stomach.
That is just awesome. Anyways, Mr. T is gonna make sure you don't get out of line right there. I wish Mr. T was my dad. He's a good guy right there. Anyway, shouts to Mr. T. Childhood heroes. We gotta love our childhood heroes. He fought Rocky. He beat Rocky. He beat Rocky in Rocky 3. Go check out Rocky 3. So anyways, the T distribution. Mr. T is what? Sure, he's a nice guy, but Mr. T is mean. So why do we keep saying that? I wanted to create that memory that when you're doing the T's, why do we say it right here? Because the T will be used with the mean. 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 The T will be used with the mean, Mr. B. The T will be used with the mean. The T is used with the mean. Mr. T is mean if you're doing drugs. Anyways, Guinness beer. Yep. That was William Gossett. Create, how are we going to figure out the margin of error of this? How do we figure out the margin of error of this? Margin of error is what? The length of the interval. Well, it's not 5 this time. This time it's like 6 point... Might be 6.4. The margin of error. Check out... no, it's bigger than that. Oh, it is. Tara, wow. I don't know what I did in my head. I thought it was 77.9. Tara, 10,000 points correcting Brian. I don't know how I misread that. I thought it said 77.9 or something, but I think Tara's done it correctly. Take half the length of the interval. I was looking at it again after Tara gave the answer. Half the length of the interval. Tara did it like that. Justin showing the mathematics in the chat. Half the length of the interval. Easy. Solve right there. Great job, Tara. Big points correcting Brian right there. A confidence interval is made from a blank to estimate the truth for a blank. We just talked about this earlier. It's made from a sample to estimate the truth for a population, and you can see it in many of our equations where it's made from the sample to say I am 95% confident the true proportion, which means the truth for all groups right there. Made from a sample to estimate the truth for a population, which is the truth when we say I am 95%. Oh, no worries, Justin. We'll throw you some points too, Justin. Justin, we're here to practice. The more we say it, the more we remember it. That's why I repeat things multiple times. I know I'm just saying it and saying it and saying it, but you have to repeat things. You have to repeat things, then you get better at it. The success failure condition for a confidence interval for proportions requires that there must be what? At most, hey, Lachey, good to see you here. At most or at least? Are we saying we can't have more than 10? Or we need at least 10? That's correct right there, Justin. It's at least. The 10% is you can't sample more than 10%. The success failure is you need at least 10 successes, at least 10 failures. And great job. This is why I can't get... yeah, Blake, right? And the good news is if you... I saw that 8 right there, and I thought I messed up. I thought I missed one of the questions. Repetition. So we'll do some chapter 14 here in a second, but at this point, I hope you're good enough to be able to fly through these and be like, we don't use bar charts because they're categorical. No matter what the shape of the population is, as long as we have a sample size greater than 10, we include the sample distribution is approximately normal. No, if the distribution is very skewed, that'd be wrong. Half the length of the interval is going to be the margin of error. So margin of error is half the length of the interval. And so it's 4. Should have been able to see that. The only way to change the margin of error is change sample size. No, you can change your confidence. The confidence is part of the formula for margin of error. So if you lower your confidence, margin of error gets smaller. If you increase your confidence, margin of error gets wider. So that is false. You could change sample size or confidence. And confidence intervals are made from samples to estimate the truth to our population. And we just did it there in like a minute. So that's what you want to be able to do. If you get to that point where you understand the problems and understand the theory, don't just memorize them. Be able to understand kind of what each question is asking and how it relates to the formula. Let's head back to the main screen. That was the speed run of speedruns right there. That was the true speed run. Doing some chapter 14. Student looked at the annual compensations of CEOs. Fun stuff right there. Let's do it. Is that the quiz? Quiz. A study you looked at. Great job, Justin. A lot of good work here. Okay. How do you recommend people to start on a project? At a certain point, you would start. I would just start. You don't want to do the executive summary first and the future research. I would start by seeing which tests you can do. We can also do some of it during office hours if you want. Just feel free to ask, like, how do you do this portion? And we could get started on that. I would look over it, and whenever you have questions, just let me know. It's the number one way to get started on the project right there. Just start going through and being like, how do you do this one? Because I think there's a good bit we should know. Because a lot of the project is based on your data analytics. So a lot of the project questions are going to be very similar. Like, oh, I have to make a confidence roll. I have to do a test. So you should have good knowledge on how to do a lot of them. We can take a look at some of it. Do you know how to make the homework? In Canvas, I don't know if there's a way. Go to my Pearson. So go to my Pearson and log in right here. And Roshni's got one too. Try going through my Pearson. Go through my Pearson and try that. Then it'll be full screen because it drives me crazy too. Like, I don't know how people work in tiny little windows. Like, I gotta have everything full screened. I gotta be full screened. Here we go. Ooh, this is an interesting one. Oh man. Oh, whoa. Wait, I've never done this one. Yeah, of course, Tara. Chapter 14 quiz, is it? There's a bunch of new questions here. Brown's gonna get stumped. I need more coffee. I need all the coffee. Let's do this. Here we go. Okay. A study looked at the annual compensation for 800 CEOs, for which the true mean and standard deviation were in blank and blank, respectively. The simulation drew samples of 30, 50, 100, and 200 with replacement from the total annual compensation of the 800 CEOs. The summary statistics for the simulations are shown in the accompanying table. Oh, okay. Well, I need to talk to Terry about this question especially. So they're showing you, this is very similar to what we've done previously. And I'm not a big fan of this one right now because this is chapter 14 from the previous test. And So the mean should stay the mean. I don't know why this is on here, because this is for confidence intervals. I don't know why. I might have to make some adjustments to this assignment, because this is for confidence intervals, and this is the formula. I'll write it down right here. That the mean for, because this is sampling distribution. That's what this question is doing about. Ban it? I might. Yeah, I might. Because this is the formula that the distribution of the sample mean is normally distributed with a mean of mu and a standard deviation of sigma over square root of n. So what they're telling us right here, ban the question, I love it. We updated some questions this semester or some quizzes, and this one's so they are telling us in this problem, so maybe someone else in another class, because I'll probably ban this here in a little bit. What? There we go. What they are telling us in this question is this. So the standard deviation is going to change, or what rather the standard deviation of the mean, which is the second part of the equation right there. The first thing you see right here is the mean for the distribution of the mean, and the second thing you see is the standard deviation. But the standard deviation of the mean is not the standard deviation of the data. It gets smaller by a factor of square root of n. So really, they're just asking us for some big calculations right here. Let me show you how to do these calculations. So the mean is always the mean. The mean just stays the mean because it's what we expect to sign in. Just sign again. Oh no, that's weird. Yeah, send me an email. I can get you in contact with our Michelson rep. They're really great and they help out students. You might have to contact them. They'll tell you exactly who to talk to. But they're really great. Shout out to Kathy Neuter right there. She's really awesome. Yeah, she's great. She's been a great help for everything. Okay. So what we are doing is we are taking, I'm going to write this one down. Where's that big number? I'm going to write down the first one right here you have to solve by hand. It's for a sample size of 30. So we are literally going to take this equation right here and plug in 18362.66, that's a 2, over square root of 30. Does that make sense what I'm about to solve? And the only thing that will change as I change these answers is what? What is the only thing as I work through the remainder of these? What is the only thing that will change as I change these answers? For 30, 50, 100, 200. What is the only thing as I work through this? The sample sizes, right? So that's the only thing that's going to change is I'm just going to change what I'm dividing by square root of. So the top, okay, so we got to go here. We got to do 30 square root. Let's clear it. 30 square root. And you know what? I'm going to cheat. 18362.66. Got it. Okay. So then we take that. Just grab a vector. Might work. I think it's right. So is the numbers 30, 50, 100, 200? Work smarter, not harder. So there is all the mathematics right there. You just take it and divide it by those numbers. We should be seeing about the same numbers. There it is right there. Pretty similar, pretty similar, pretty similar. Simulations will mimic what we see in the data in the actual results. So the simulation looks pretty accurate. And that's what they're going to go for at the end. I'm not a huge fan of this question if you can't tell. But just a bunch of solving math right here. We do like math, but math is just something we use. So why do it all by hand? 2 decimals. You got to be kidding me. Is my R not rounding, or are those the answers? SQR30. There's no way that round. What? No, R's rounding it. I was trying to work quicker. There we go. And now. I was trying to work quicker, but then. There we go. Yeah, just and so it does everything make sense what I'm doing right here? I'm using just the software to help me solve the answers to make it just easier on me. You'll know you're getting the problems right if your answers are very similar. I was changing the global options inside of R on how it does the scientific notation and woo! Quick, get it done right here. Ban the question. Yeah, I think we'll go back in here in a moment and because this is sampling distributions. It's not bad knowledge, but it's sampling distributions. The theoretical values of the means are roughly, oh no, they are exact. No. They're roughly reasonably close to. They're not going to be exactly because the simulation's not going to do the exact same thing as the truth. Simulations will mimic reality. The theoretical standard deviations are reasonably close. They're both reasonably close to it. Yeah, should be right. Woo! So the biggest part of this problem is knowing that when you do the new standard deviation for the distribution of the sample mean, you divide by square root of n. So the mean stays the mean. So the answers down there in green are the answers we're looking for. So the mean stays the mean. So that number stays consistent throughout. My personal favorite quote is 295. I'm so glad people have favorite quotes. That really means a lot to me that people have fun and we have some quotes. Try to give everyone's many, try to give a lot of quotes. And then the standard deviation gets smaller by the factor of square root of n. And then just make sure you type everything in the right way. So I use software to do it to get the exact answers, but you can just type it into the calculator. As you can see, there's the first answer right there, 3,352.56. It'll give it to you, I guess, with the decimals, but R is going to carry more. Ban this question. No, that's a real question right there. There's a question with two more parts in its research measures the way size. Yeah, those shouldn't be in this section. That's sampling. That's sampling distribution stuff. That's gonna be very similar right there, and it's gonna. So we could do that one, Tara, and those shouldn't be here. Those shouldn't be here. You know what? I might go. I'm gonna go ban those questions right now. But if we ban them right now, we can't do them during office hours for another class that doesn't ban them. And I need to message Terry about this too. Ban them. Here, let's do another question. Then we'll maybe ban them at the end. We probably won't have time to do the waist size one. Is it the researcher who investigates waist size? Is that the one? Is that the next one? A researcher investigates. Oh, here it is. Okay, this one we got this. Look at this. Look at this. It's about Pizza Hut. I thought we had some Pizza Hut right here. So save the other classes. Yeah. So we'll try to. That's because I could always refine them. Well, it'd be harder. I'd have to create the question somewhere else so I could do it. Like if I remove a question, it'll be harder for me to get back to it. I would just have to, I have to be careful because I wouldn't want to create an assignment that students had to do. Okay, here we go. Evan's here. Where's Evan at? We need Evan for backup. Okay, a researcher investigates whether the mean cholesterol level among those who eat frozen pizza exceeds 220 milligrams per deciliter. I think that's what it is. The value considered to indicate a health risk. The confidence interval for the mean is this. Explain what this indicates for the health risk. Okay, so how would you interpret this? This is all I'm asking for you right now is to interpret this interval. They're trying to figure out the true cholesterol level of people who eat frozen pizza, the true mean cholesterol level of people who eat frozen pizza. Good to see you here, Rosemary. So don't even worry about what the question says. I want you to write an interpretation. 10,000 points to the first person who writes the correct interpretation. I know Blake's been practicing all day. We're trying to figure out the true mean cholesterol level for people who eat frozen pizza, which is me. So we're trying to figure out the true mean cholesterol level for people who eat frozen pizza. Pretend 95% confidence. They should have given confidence. You give a confidence interval, you gotta say what percent confidence it is. Probably 95. It's the most common one. So how would we do this? And I'm doing this because this is part of the test. Being able to interpret a confidence interval is part of the test. Would you, so that would be to find the margin of error. So if you want to find the margin of error of the interval, the margin of error is half the length of the interval. So if it said find the margin of error of this interval, we could do the following, and the margin of error is 8.15. So how would we interpret this 95% confidence interval to estimate the true mean cholesterol level of people who eat frozen pizza. So I am 95% confident. Blake, but wait, watch out, Blake. The true mean. But then you got to give the context, Blake. So this one's a little bit longer. So Blake, we're going to still throw you the points. But so listen in on this. And this is why this one's a bit longer. I'm going to throw you those 10,000 points. But listen into this. You ready? Here's the interpretation. So Blake's got part of it. And I think Justin might have the rest. Ooh, Justin. Justin's got the whole thing, I think. Got to throw more points. Justin said, oops, I think, did Mubot catch that? Mubot didn't. Okay. I am 95% confident that the true mean cholesterol level of people who eat frozen pizza is contained in the interval blank to blank. You got it. 220.9 to 237.2. So think about this. That interval is completely above 220, right? Is that good or bad for these people? Just put good or bad in the chat. Because we think the true cholesterol level of these people is somewhere in this interval, which the interval is completely above 220. Is this good or bad? It's bad. Because now we're like, ooh, we think the truth for you guys is that for the average person who eats frozen pizza, you're above this. So because we're trying to estimate the truth for the average people who eat Cheerios. Cheerios goes some good stuff. Cheerios is good stuff right there. Shouts to the bee. That's the Honey Nut Cheerios. The confidence interval is entirely above this. Therefore, the mean cholesterol level for those who eat frozen pizza indicates the average person. Therefore, the mean for those, the average person who eats. That'd be it. Boom. That's a very good question. Wish they went into more detail. Morgan, great to see you here too. Wish they went into more detail, but that's a good question. We only have one more lined up right now. We only got in 1882. I've only got that one. So please, if you have another question, here it is. If you have another question, let us know. This is looking like a good question right here. Let me take the timestamp on this. In 1882. I always try to go above and beyond these questions so that way you can get more information than you need for the question. You can have the information you need for the test. Okay. Here we are. Not a bad question. I agree. Like, don't ban that question. In 1882, A.A. Michelson attempted to measure the speed of light, an important experiment in the history of physics. The values given here are in kilometers per second and have had 299,000 subtracted from them. He reported the result of 23 trials with a mean of this and a standard deviation of this variation. That's a high amount of standard deviation. Find a 98% confidence interval for the true speed of light for these statistics. Okay. They are not... because they're saying... Okay. Let's see. Oh, man. The adjustment is, I'm wondering, like, where are they going to go with that? So if we want to make a confidence interval... Ooh, he wouldn't have been able to do this because Gossett hadn't done Gossett T yet. You were Justin. I forgot to add. Do you have to add back in? Oh my gosh. Yeah, I'll give you the points back if you didn't do that, Justin. Justin, seriously, right here. If you've already done this quiz multiple times and you just let me know, message me. Hey Brian, I forgot to add in that because they want, because that's what they're getting at the end. You're right, Justin. So just let me know. Like if someone misses it because they didn't add it back in, this is fine. It's a tricky question. You did the work. What do you need to know to get these problems right? What do you need to know? Notation.
Notation, brother.
Identify anything in this problem. Notation, brother. Identify anything in this problem. Degrees of freedom equals 22. Nice job right there. Already going for a trickier one. Degrees of freedom is n minus 1. And then Justin has also identified n. And so great job right there. Confidence level. Not quite p-value. It does say p-value in the app. So sorry if that's caused any confusion. You could say level of confidence or critical value is associated with 98%. P-value is usually considered for tests, but percent of area shaded under the curve is sometimes in the apps referred to as p-value. But we would probably say relative to a percent confidence or things like that. And the t-statistic, great, Justin, you are destroying this. Great job. That does sound about right for the t-statistic. So the t-statistic, Justin's already going for the really hard ones. The t-statistic, we need relative to a certain confidence. And so when you do the t, you have to know the degrees of freedom. So we're going to go over here and get the T statistic right now from the T applet. So we have to go over here and put in 22 degrees of freedom. Why 22? Some people say, why'd you pick 22 degrees of freedom? Why 22 degrees of freedom? So the degrees of freedom are n-1. Why 22? You have to know that the degrees of freedom show you the shape of the T, 23 minus 1. So this controls the shape of the T we are building. So the more degrees of freedom it is, the more normal it is. The less degrees of freedom it is, the more stretched out it is. So we have here a T distribution with 22 degrees of freedom. And then we go right here and we go to the in-between and we do 98% right there. And we get exactly what Justin said, 2.508. Make sure it shades the in-between from the lower to the upper. It does say p-value right here, which could cause some confusion, but it probably should be read that this is relative to a 98% confidence or the middle 98% shaded under the curve. So that is the T, 2.508. T. It's not p hat though. Exactly, it's not p hat. And so there's the T, the standard deviation. Just remember that standard deviation starts with an S. Easier way to remember that one. The mean is Y bar. The bar, oh, whoops. The bar is what indicates, oh, that purple. The bar is really what indicates mean. Like X bar is the mean of X. Y bar is the mean of X, of Y. So Justin's got a lot of great work. Thank you, Justin, in the chat right there. We've already got a lot of this marked right here so we can see where the notation is. Knowing the notation is going to be huge. The T is usually the hardest one for people to find. So 75.6218. And then standard deviation. And what do we get? Tell me if you'll, and then we have to add back in that constant is what Justin's saying also. So don't forget to do that after you make the interval. Okay. So 23. $812. Oh my gosh. $812. Yep. There we go. I don't know if you got the same, Justin, but I hope you did. And let's go take a look. Okay. So we need to add back in that constant right here of 2999, 299,000. Okay. Oh, so it's going to be just these numbers. And then, is that right, Justin, right there? So you just add, because it's going to be, those are the last digits right there. And that's interesting how they did it. I guess it works out. It's a constant, yeah. So 299, 7, 2 decimals. That rounds up. So many decimals. Ah. And the other number is... That should be right. Let's hope I did my right. Working alongside you, I have different values. Yeah, I think so. So you should get something like this right here. That seems accurate. And I guess that's a small amount of variation compared to the size of the values when you look at the standard deviations now. Yeah. In other words, what does 98% confidence mean? I am 98% confident the true mean of light is contained in the interval blank to blank. With 98% confidence based on the data, the speed of light is between the upper... Yeah, with 98% confidence. That sounds about right. Any measurement of the speed of light will fall. No. The confidence interval contains the true mean. No. not this confidence interval. It's about the process. It's not about one interval. It's about multiple intervals over the long period of time containing the truth. So it's not about this confidence interval. Yeah, for all samples, 98% of them will have a mean speed. No, the truth doesn't fall in the interval. With 98% confidence based on the areas realized between the upper and lower. Yeah. I wish they just said I am 98% confident the true mean is light is contained in the interval blank to blank. What assumptions do you have to make? Here we go. This will be fun. The measurements are independent. That sounds about right. No. The measurements arise from a random sample. Stupidly random experiment. The data follow a distribution that is nearly normal. Okay. Nearly uniform. Whoa. No. They're trying to trick you right there with that. Uniform means flat. So what are our conditions right here? Now, when I teach the test, I want you to know what conditions to know. Condition 1. What is condition 1? Condition 1 is always what? Random. Did we randomly, can't even spell random. Did we randomly take the speed of light? That also goes with independence. It's an assumption that each measurement is independent of previous ones, which would mean they're random. Like if they're not independent, then they're dependent and they're not random. So independence is also kind of part of randomness. So that's why I check the independence. Condition 2 is 10%. It's always 10% because the 10% says we need to sample less than 10% of the population. Since the speed of light could be measured indefinitely, you can't oversample here because it only works for finite populations, this condition, such like sampling UT students. You don't want to sample more than 10% of UT students. The last condition we have to pause because now this is quantitative. So we have to ask, is it quantitative or categorical? And the third condition right here is nearly normal. And they're trying to trick you with that nearly uniform because nearly uniform is flat and we don't want uniform data. We want nearly normal for the T. So if it wasn't quantitative, it would be success failure. There are a few others we'll learn later on, but at this point we only know the nearly normal and the success failure. The data follow a distribution that is unimodal and reasonably symmetric, and that's where we're getting there. Little worried. 100%. Always a little worried, but not too big of worry. Well, that's got it right there. It's a pretty good question. I give it a moderate seal of approval.
I am Mubot.
We took off the approved sign. So, woo! Did you get it right too, Justin? Great work. These are tougher ones. What else should we do? We got time at least for one more. Waist size. It's just cat. It's just. This is the exact same as the previous question. The theoretical means are reasonably close. Looking at the histograms at what size? I think it's a sample size of 5. Yeah, it's 5 because it's basically, since the data is the smallest sample size, which sample distribution is due to the most metric. What about the shape? They are unimodal and nearly symmetric. So the sampling no. There we go. And the mean should be the mean. So 6.0203. And the standard deviation is this 4.028. Would I start this like 2 minutes ago? So 58, 23. This is a question that shouldn't exist. So and we'll do software next. You got it, Justin. Doing it really quickly right here. So 2, 5, 10, 20. We are dividing just like we did. Check out the previous problem where I walked through more in depth on this, where all we're doing is dividing the original standard deviation by the square root of n. The mean stays the same, so you're just taking the standard deviation right here, dividing it by square root of n. As n gets larger, the standard deviation gets smaller. And so I'm just taking those values in the program right here to do it a lot quicker. 4.028. How many decimals? 3. Oh, I gotta rerun the code. How dare they? And your answer should be close to the values. The mean stays the mean because if we know the truth, we should expect to see the truth. And the mean is the truth. We'll do one more here. I think that's got it. I did this one really quickly. I'm only worried about that sample size of 5, which I think is a little bit unfair. There we go. Done. So that one's the longest part of this one is doing this step right here. You can also look at your work with the answers here to see if they're similar. The mean should be exact because the mean is the mean and it stays the mean. The standard deviation is the original standard deviation over the square root of n, so it does get smaller as n gets larger. That is how it works. Software analysts. Let's do some software analysts. I'd like 5 parts asking. Oh, yeah. Let's see. Software analyzes of the salaries. Okay. Well, chill music right here. Here we are. Oh, it's good. It's a okay, so this one's an interpretation one. This is all about proper interpretation. I love it. Okay. Taking the timestamp. Let's do it. So when you are interpreting these, don't start reading their interpretations to start. Interpret this properly. So I want you to take a moment right here. If you're watching this, please do it. Try it. Write down in the chat or on a piece of paper right now, and Blake has the start of it. I am blank percent confident that through blank is contained in the interval blank to blank. It's technically just interval singular. So what would we put in here, Blake? What are we going to put in here? So try to use this information as though it's a test right now to try to answer a test question that says interpret this interval. What are we trying to figure out? So try the whole thing. Pretend it's a test and be like, this is a test. How would I interpret this interval? Remember, we're going to do interval interpretation and test interpretation, like hypothesis test interpretation. So you want to be able to do both. You want to be able to do interval interpretation and hypothesis test interpretation. So this is your interval interpretation right here. It says interpret this interval. So don't even worry about what it's asking yet. Know how to interpret this. So I am. And then we have to put our confidence level. I'll give it a moment here or two more. Because if you practice it and can get it down, then you're good to go for the test. If you're like, oh, they want me to interpret a confidence interval, we have to use what Blake has in the chat right there. I'm going to pin your message, Blake. Oh, Lindsay's got some good stuff. Let's see what Lindsay put. I am 90% confident. The message is currently blocked because I pinned a message. I am 90% confident. It's really close right there, Lindsay. Good work, Lindsay. We're going to throw you some more points. You're missing a little bit of context. That might be like 3 out of 4 points. I think Blake has some more context. I am 90% confident that the true mean of Nevada's teachers' salaries is contained in the interval blank to blank. Yeah, don't worry. That's why we practice it. And so great job right there. Like when you get to test, you're like, oh, I got to put that context in the middle. That's usually what people forget. And that's not bad, Lindsay. Like 3 out of 4 is not horrible for the interpretation questions, which are usually the hardest part for people. So good. Lindsay, we're throwing another 5,000, make it that 10,000 points right there. Yeah, that's why we do it. So that way, when you get to the test, it's like, okay, I am blank percent confident that the true, and then we got to figure out if it's mean, proportions, difference between means, and then we give the context of it, and then we give the intervals. So the more you practice, the more you get it down. Like put in the comments right there. So that is what we're trying to analyze, the true mean salary of Nevada teachers. So let's see what the question asks. If many random samples of 288 teachers from Nevada were taken, about 9 out of 10 of them would produce this conference roll. No, it would produce conference rolls that contain the truth. The conclusion is incorrect. About 9 out of 10 conference rolls will contain the true mean salary, but samples of 288 teachers will produce different conference rolls. Yeah, they're going to make different conference rolls. Different random samples will produce different random confidence intervals, and about 90% of them will contain the truth. It won't produce the same conference roll. About 90% of 90% conference rolls contain the truth. If many random samples of teachers from Nevada were taken, about 9 out of 10 of them would produce conference rolls that contain the true mean salary of all teachers from Nevada. This does sound accurate. About 9 out of 10. No. No. All 10, no. The conclusion is incorrect. About 9 out of 10. No. This is correct. If many random samples of teachers from Nevada were taken, about 9 out of 10 of them would produce a confidence interval that contained the true mean salary. That is correct right there. That is the theory behind how confidence intervals work, that if you make 90% confidence intervals, in the long run, 90% of 90% confidence intervals will contain the truth. So it's just changing the number right here to 90%, which is in the notes. We expect 90% of 90% confidence intervals to contain the truth. 13 minutes. We'll end here in about 3. About 9 out of 10 teachers from Nevada. No, this is about the mean, so that's incorrect. This is an incorrect conclusion. The interval means no. This is incorrect. The interval is for the sample mean. No, wait. Are these newly hired teachers? No. This interval is incorrect. Here it is. This is the one. The interval is for the population mean, because we're trying to estimate the truth, not the salary of individual teachers. So it's not about an individual teacher, and it's not about the sample mean. We know what the sample mean. The sample mean's at the center of this interval. The sample mean is if you average these two values, and it's good to know this, if you take 4, 3, 4, 5 right there, 4, and then add to it the upper of the interval, you can get the center of the interval by dividing by 2. So this is the sample mean. Now, that's not the true mean. We're trying to estimate the true mean, but the best estimate of the true mean is the sample mean. And we were talking about this a lot earlier with the following formula, that the y bar is at the center of the interval. That is the estimate. And then we do plus or minus a margin of error. Just like p hat here at the center, y bar is at the center of the interval to estimate the true mean. So good question right there. About 9 out of 10 teachers surveyed earn between, no, we're trying to estimate the true mean. The interval, the conclusion is incorrect. The interval is for the population mean salary, not the individual. Yeah, I think that's down. No, the conclusion. The interval is for the, no. It's very similar to, oh wait, did we skip one? About 9 out of 10 teachers from Nevada earn between this. No. The conclusion is incorrect. The interval is for the, they're really hammering down that this is for the population mean. They really want you to know that. We are 90% confident that the average teacher's salary in the entire country, now that's a scope issue, it's not for the country, is between this and this. So that's the wrong context. So they're purposely messing up the context right here. If this said, real question, I don't think I have a good example of one. Good question, Blake, right there. We'll have to do it maybe next office hours. We'll do some project. The conclusion is incorrect. The confidence interval addresses only salaries of teachers in Nevada. This is a scope issue of context. Wow. A little bit scared. Can you please go over the... Yeah, we did that. So Catherine, check it out. Rewind the video if you want, if you're in our section coming up here. But check out the earlier portion of the video. We did Canvas content for the first 33 minutes, and we did that problem a few times. And Blake's offering some help right there on the equations to solve it. So we did Canvas content, I think 3 times. Yeah, no, thank you so much for asking, Catherine, because we got class here in 10 minutes. So Canvas content was at the start of this video, and I'll drop, you know what I'm gonna do right now? We're gonna end the stream here in one moment, but while we're watching here and doing this, I'm gonna go right over here, and I'm gonna go to edit video, and under edit video, it's loading up. We're going to drop in these links here right now. The links are in. So if you reload this video, I'll be ending it here in a moment. The timestamps are in the video. I always try to get them in pretty quickly. I used to do it at night, and I'd be sitting up at night putting in timestamps for like an hour. But then I started to take the timestamps while I was doing the video, and then I can just pretty much do it right after class, or when I'm like, oh, I have a free moment, let me upload the timestamps. Just got to go to edit video and drop the timestamps in. So that's why you always see me taking timestamps while we're doing stuff. It's way easier. It's way easier than going back and rewatching yourself teach all night. Yeah, sometimes I'll be watching for like an hour or two. It's like, okay, I taught for 4 hours today, so let me find the timestamps. 2M will be reached today. You got this, Blake. Until then, bye for now, everyone. Bye!